Good afternoon. It's my turn to run the show for the next 3 hours today. I know it's the fourth day of the summer school. It's afternoon. It's warm outside, right? But trust me, I'll do my best, and I think it's going to be pretty exciting, especially if you prefer looking at me and the slides than the hypnotizing laptops you have in front of you. It's also, to be honest, a good indication for me to see your faces, because then I know if something gets across or comes across, or if I should repeat that, right? So looking into your eyes helps me as well. Okay, so today we're talking about data-driven applications for power system security assessment. So we start with, let's say, a little quiz. So by spotting the differences, do you see any difference? Was that? You can use a microphone. Do you see any difference? Yeah. You can throw it. I think it's better because we have. Yeah, throw it to me.
All right. Well, the increase in the electrification.
Yeah, this is one. To be honest, this is more resolution of the image, but you are right. It looks like this. Yeah. Any other differences? Yeah. Go back.
There is a blackout in, what is it, New England?
Really? Yeah, it is. Yeah. New England, New York, right? You see this?
Oh, yeah.
It's a black spot, guys. That's where New York is. As this must be the brightest part of the US, right? Yeah. So we're talking about the 2003 blackout. The 2003 blackout actually affected 55 million people by cutting the power for almost 2 days, and had a cost of $7 to $10 billion, right? And this is because actually many events happened that were not foreseen or were not planned for, and the security assessment failed. So the job of every operator is to make sure that these things don't happen, right? So when we say about optimization and we try to minimize the costs, and we try, let's say, maybe, so a good optimization algorithm might manage to get us, I don't know, a couple of millions, maybe $1 billion a year, less cost if it's like something really, really new. We're talking about $7 to $10 billion lost within 2 days. And that's why Johanna was also saying that the first priority for an operator is to make sure there's no blackout, okay? First, they make sure there's no blackout, and then they try to optimize their system, and then they try to minimize their costs, okay? So the power system security assessment is very, very important for the operator. And they need to find ways to ensure that these things don't happen. So let's see a bit at the statistics. So in the US, this happens about 1 hour per year on average. Of course, this blackout actually increased this average by a lot that year. It is estimated, so there was a Berkeley National Lab report, 2005. It was estimated that about $80 billion a year are lost because of power interruptions, not only because of those blackouts, but small distribution networks, they might have some interruptions. $80 billion. And this, when you compare this to about $370 billion, that is the market for the US, so the cost for electricity, it's very substantial, right? So blackouts don't only happen in the US. There's also the India blackout 2012. This affected 700 million people, okay? The more dense the area is, I mean, the impact can be much larger. So the main, let's say, characteristics of blackouts is that they are rare events, but if they happen, they impact a lot of people with severe consequences, okay? So what operators try to do, and what we try to do also with our methods, is to identify how we can make sure that we are always safe. So how can we assess the security of different operating points? So here is the how things look for Europe, because we are in Europe, right? And this is the average interruption time in minutes for different European countries. So I have here Denmark, because that's where we are. And we are very happy that we are actually less than 50 minutes per year. This means half an hour per year that have interruptions. I mean, you can see more or less all the different European countries, how they perform. This is for year 2012 or 11. Okay. You can see that, okay, besides Latvia at that point, I mean, all the rest, yeah, they might be like 5 to 6 hours, less than 5 to 6 hours a year. Okay, yeah.
How do you count here? How do you count here? Do you need a minimum area to count these minutes, or because you can have an interruption just in a village, and then does it count, or?
Yeah, it's the average. Yeah, it's whatever. So wherever it was interrupted, wherever supply was interrupted for some time because of some failure.
Okay.
Yeah, it doesn't need to be. It's not going to be, of course, the whole country, right? Yeah, these are where customers have been experiencing interruptions. Okay, so what do operators do in order to be able to assess the security of the current operating point, also for operating points that might happen in the future, right? So they have this contingency list. They call it the critical contingencies or credible contingencies, if you want. So these are things that might happen. Contingency means, for example, that this line, if this line goes out, then I'm going to miss part of my generation, right, or part of my supply. So they have this contingency list. They run it every 15 minutes on average, depending on the operator. And if the credible contingency becomes critical, this means that if this happens, then we have a problem. Then we have to have remedial actions, right? And usually they take that preventively. So because the system must always be n-1 secure, if something happens, I have to be prepared so that if we have a line out, I won't have any consequences. So this n-1 security is somebody that hasn't heard about n-1 security? Yeah. Okay. So n-1 security is, so we have n number of components, right? And my system must be safe even if I lose one, right? So I lose a line, and I still must be able to supply all my load with power. I lose a transformer, the same. I lose a generator, the same, right? For every single component, if I lose it, I must be able to still supply the load. So I run this contingency list. Usually it's called n-1 contingency analysis. If for any single outage I have a problem, I have to take some actions, right? And then they're also looking about n-2 sometimes, and of course stability assessment. And that's what we talk here also about dynamic simulations. Power systems are dynamic systems. They change in time. If you put a disturbance in a dynamic system, there's going to be a response, and you don't want to go outside your component limits. Okay? Good. So these are now the challenges, right? First of all, dynamic simulations are hard. I don't know if you have ever run a dynamic simulation. This is like a time domain simulation, transient response of a dynamic system. Here we're talking about systems with thousands of buses, right? We're talking about tens of thousands of different parameters that you have to tune, and this must reflect the real system. And now thinking about how many operating points you have. So for a single load snapshot, in the IEEE 14 bus system, right? 14 buses, 5 generators. If you take a granularity of 1 megawatt, so if every generator can change their operating point by 1 megawatt, you get 2.5 million possible operating points. How many of them are safe or feasible? It's another question. But you have to assess about 2.5 million operating points for a single load profile, right? And that's for a very small system. Imagine what happens in much larger systems, right? And so so that's why operators try to find different ways to make that smarter. Then of course we have n-k. So n-1 is the standard practice. Some go to n-1 less than 1, and they try to take some risk measures, right? In order to assess, maybe I don't need to consider the outage of this line because the risk is very, very low that something will happen. And the last one is that the safe operating region is a nonlinear, non-convex region. So what do we do? What are your ideas? I mean, you're engineers. These are the challenges. What do you do? Backup? What do you mean by backup? Yeah, give it to me and I can throw it to him.
You can have multiple lines, parallel lines, so you can switch between them if you have outage between one line.
Yeah. So my question was more, how do you assess the security of a system? Not what are you going to do so that you're always safe, but rather, how do you perform the assessment? Because you have to somehow perform a security assessment, right?
Then you can see the biggest contingencies that you have, start from there, and then go deeper into smaller contingencies.
Yeah, yeah. So identify the most critical contingency and go from there, right? Yeah. So this is one way. To be honest, my question was more general. So what are the family of solutions that we can consider for doing the security assessment? And actually, there are not a lot of options. The first is perform simulations. You have to perform simulations to assess the stability of every operating point. Now imagine millions of simulations that have to be performed, right? There is a different family of methods that actually emerged in the 1980s. It has been revived recently, talking about stability certificates or security certificates. So what you do there is you take your dynamic, nonlinear dynamic system, you try to approximate somehow. The newer approaches also include the nonlinearity, so by Kostya Turicin and others. And then you try to extract sufficient conditions. Okay. So analytically, you try to, this is the Lyapunov certificates. If you have some control background, you must know about Lyapunov functions. Okay. Any of you that does. So you try to let's say, extract a certificate that, you know what, if these conditions hold, then I'm going to be safe in this region around the operating point. And in this way, you can actually discard a lot of simulations because you know that this region where around this operating point is going to be safe. So if I need to do any simulation, it's going to be outside the region to assess that, right? And the last is machine learning approaches, which, to be honest, besides decision trees, haven't really found traction in power systems at the moment. Okay, but that's what we're going to talk about. Because now we have new tools and new methods, and this might be something to consider for the future. Okay. Decision trees have worked well. They have been applied in the industry. We're also going to talk only a bit about them. Okay. So this is the setting. Any questions? Good. I'm done. Maybe I have a couple of more presentations. Power system security assessment. Okay. Just want to give you a bit of a background, what exactly the problem is. Is anybody not familiar with power flow equations? Good. Yeah, well, it's good for me to know. It helps me when I talk. So power flow equations are actually quadratic equations that connect power with voltage, the square of the voltage, right? You can think of it like that. If you have this as an equality, for example, in optimization, it's a non-convex problem. So we're talking. So these power flow equations, they define a non-convex and non-linear, because it's also quadratic, feasibility region or stability region. Okay. Now, if you put on top of that also the component limits, so imagine that you have reactive power limits, voltage limits. You can think of a sphere, and you just cut part of it because of the voltage limit, right? So the nonlinearity of the power flow equations and the component limits make the whole feasibility region, so the safe region where we can operate, a non-linear and non-convex region. Okay. So let's say that it looks something like that. Okay, that's a non-linear, non-convex region. And that's only steady state. That's only to make sure that we have a balance between supply and demand. Okay. So I have my loads. My loads ask for some active and reactive power, right? And then I have my generators that they must supply this power. They must also supply the power that is going to be consumed as losses on the lines, right? And they must also keep the voltage within reasonable limits, right? So all these things must happen. So this is just an equilibrium we call it. A safe, not a safe, an operating point that satisfies the AC power flow equations. Okay. Now, on top of that, then we have the n-1, right? So now we have also to consider what happens if we remove a line that we still must remain inside the safe region. So all the limits must not be violated. Okay. So n-1 reduces this area. And on top of that, we have the stability, which is, I haven't changed it. Okay, it looks like that. So yeah, on top of that, we have the stability, so it's a different region, and then we have to take the intersection, and that's the intersection. Okay. So when we talk about optimization, power flow, or optimal power flow, we almost never consider dynamic stability, right? And even n-1, to be honest, can be quite challenging. But the reality is that our operating point must be in this small region. That's the reality. That's where we should be. Okay. So our main challenge right now is to identify this region. Right? What would you do? So let's say that you must think of it, this is like a two-dimensional, right? But we're talking now about thousands of dimensions here. So it's like really moving somewhere, and you don't know where you really are. Indeed, actually, because we have generated some databases, you are completely blind. So how would you actually try to identify the region? So what would you do? I'm not looking for a smart answer here, right? I'm just looking for an answer. So, you have this problem, so you have to identify this region, but you don't really see how it looks like. Let's say that we need to generate a database a bit smart. Yeah? Do you have?
The two-dimensional case.
Yeah. Give it to me.
For the two-dimensional case, maybe you could run simulation, then use projection to approximate this region, roughly. But then if you go to higher dimensions, and then you have to account for stability.
So if you had to focus in one area, or not in one area, let's say, if you had to focus somewhere, where would be the deciding area to focus? And I'm not asking this question very correctly, but I don't know how else to formulate it, to be honest.
Place where your system is most weakest. If there is the weakest point of the grid.
So the place where the system is weakest. Yes, but you have to know where this is, right? Where the place is weakest. So I'm not formulating the question correctly, so I'm trying to answer it. So the boundary, right?
Yeah.
Important is the boundary. So when you change from stable to unstable. If this was a convex region, if I had the boundary, then I know all the points inside my region, right? The problem is it's a non-convex region. So I still need to assess also points inside and outside my region to really understand how this looks like, okay? So the problem gets really, really difficult, even for generating the database. And if you have time, and I hope we will, I have a couple of slides on a method we're developing here at DTU on how we can do that a bit smarter, okay? So I talked about stability, and stability actually is not only one thing. Stability is like a series of different things, and the operators must make sure that their system is stable against everything. Transient stability, small signal stability, voltage stability, frequency stability. Okay. It gets really hard. We have trying to be developing databases that cover this, which is the steady state, and the small signal, here the small disturbance, angle stability. But imagine what else is left and how many things you have to check for. Okay. But that's why, so it's a lot of data. It's a really big, huge dimensional space. And even with power systems are here for like 100 years, right? And even with our developments right now, we can still not assess everything. So imagine the following, right? I was telling that we have 2.5 million possible points for a single profile. Let's take 1 million points. And let's assume that you have about 1 second. So in 1 second, you can assess a steady state and small signal, which is, to be honest, a bit fast. It's going to take you 1 million seconds to be able to assess the stability of those points, right? Do you know how much 1 million seconds is in hours? 3,600 per hour? Is it 50 days? So imagine now it takes 10 seconds. Let's say it's 50 days. I don't know. Imagine it takes 10 seconds per assessment. It's 500 days, right? It's 1.5 years. So the problem gets really huge, really fast. And that's why power system operators try to operate it in a region where they know it can be safe. The reason why power systems have been working very, very well, right? We're talking about 1 hour of interruption per year, right? Over all these years. It's as Damien Ernst told me from Liège. So power systems are inherently stable. The traditional power systems with our synchronous generators, they have a good damping. So usually, so if there's a disturbance, they are going to return to something stable. The problem is, though, that we don't have as many synchronous generators anymore. We move to a future where everything's going to be power electronic based. And you can think of it as the following, right? So imagine, I'm going to talk about fighter jets. I'm sorry about that, but maybe somebody's uncomfortable. But World War II, we had airplanes that were actually flying, obeying, I mean, you always have to obey the laws of nature, right? But they were more or less inherently stable. Right now, if you get the latest F-35 or even the F-16, if you just let it fly without any control, it's going to fall down like a brick, right? So it's control that keeps them on the air or in the air and make them so agile. So we're moving to a system where control is going to be crucial, and we need to be always able to identify how things are going to evolve, right? So stability becomes an issue in zero inertia systems. Okay, so the focus of this lecture will be on machine learning approaches. We're going to talk about this decision tree. Actually, it's very, very small about my part about decision trees, but you have a hands-on exercise on that. We have prepared some code, actually, and Andreas and Leila have prepared some code for decision trees and neural networks where you can try to train one yourself. So it was first proposed by Louis Wenkel at the University of Liège. It has found industry applications. It has worked really well. So some operators use it. And research is still ongoing. And now the focus is on interpretability. So if you remember Dolores' talk on Monday, we take these insights from different fields. Now, so they also come into power systems. There's a recent paper just appeared, actually, a week ago or so, on interpretability of decision trees for power systems. Okay. Then we have neural networks, and there have been applications, or let's say, yeah, please.
When you talk about decision trees, you mean individual trees, or you mean like random forests also?
It's a whole family of these, but the same concept.
Okay, but we don't usually use individual trees. Right?
No, it's going to be yeah. Questions? Okay, neural networks. There have been applications for power system security assessment. They have never found traction. And there is some renewed interest with deep neural networks, which are neural networks but deep. Do you know what, I mean, you know what the difference is between deep neural networks and neural networks? Yeah, you just have more layers, right? More nodes. But there are also some, I mean, one of the let's say one of the developments that is not really associated with deep learning, but it has found good application with deep learning, is the convolutional neural networks. So instead of actually assessing or actually putting a weight on a single input, you take a batch of inputs, like small areas of a matrix, and you assess them all together. I'm not going to go into detail now, but I'm just saying about convolutional neural networks, and if you want, you can look it up, or we can discuss it afterwards, okay? So there has just been a paper last year that so San Constantelos and Strubats, they try to identify what are the key features that are critical for the stability of the system through deep learning, and then they use this in order to assess their system security. We also have a paper where we tried to represent systems or power systems as images. So deep learning or deep neural networks have been very successful for image processing and object recognition, right? So if we're able to represent power systems as images, then we have a whole world of opportunities. There's a huge toolbox that's now available and will also be available in the future where we can apply these tools on power systems. But the challenge there is to represent power systems in the right way as images, right? That's the major challenge. And we have found, let's say, a way. It's a conference paper at PowerTech. There's still a lot of work to be done there. Okay. And we think, so there are also some new methods that we think that they can help neural networks get a lot of traction in safety critical systems and power systems. We can discuss about this as well. But this is more or less the current state. And I'm done. Any questions?
I have one question.
Yeah. Can we? Sorry about this, but when you see the video, you'll see that's important.
Like in power system, one of the main problem for failure is the protections.
Mm-hmm.
So how do you program them? Because there's this kind of discontinuity in the operation, and they basically initiate most of the blackout, and their coordination is a key problem. So how are you going to program? Because if you put as a picture, it's a continuous picture, but the protection make them discontinuous.
True. So what we're doing at the moment is we have the snapshot, right? So you already have the settings and everything, but the question is, at the moment, so if you have this snapshot and something happens, how probable it is that this will become unstable, right? And you get an index about that. So the risk of this snapshot to move to instability based on different inputs. I must say that what we have done right now is only for N-1 and small signal. So we haven't looked in transient. I think this is a challenge by itself. And I don't have an answer at the moment how this is the ideal way to treat it or to address it. It's a very good question. I have no idea. Okay. There's another question over there.
Deep neural networks are like black boxes, right? So is it safe to use them as security tool? I mean,
yeah. So we're now working on a paper with Andreas. So it's going to be ready within a month from now on verification of neural networks. So what we try to do is to extract some kind of formal guarantees about the behavior of the network. And this will turn them from a black box. If I say white box, probably too ambitious, but let's say a gray box at least. Okay. So you try to understand how the neural network behaves and for which set points it's guaranteed to give you a safe classification or unsafe. And then you can check, right? And that's what I say with these developments. So this is a field in the machine learning research just the last 1 or 2 years. And now we are applying that on power systems, and we get very, very encouraging results. So I think that if we manage to do that well, and for that we need, by the way, optimization approaches to do that. If we manage to do that well, I think we can have an impact and get power systems industry, if you want, to adopt them. Okay. Questions? Okay. So I don't remember what I have next. It's machine learning approaches. Okay. start from the last, but yeah. So machine learning approach is a very short overview. So we talked about what the problem is. We talked about how difficult it is and that we want to apply machine learning, so decision trees or neural networks. The question is, what do we really need to do that? And if you don't know, there's at least a recipe for Dennis Brand's. So what are the ingredients? What do I need? Yeah?
Data?
Yes, we need data.
Efficient algorithms?
Mm-hmm. Yes, we need algorithms. Yeah.
Compute power.
Computing power, yes, we need that as well, and a lot of it. True. Yeah, that's it. I didn't even have computing power in my list. I should have had it. Very good. So if I want to formalize it a bit, so data, we need training data, right? So we need data that we will train our approaches, so where our algorithms will learn, and we need test data. Okay. So besides computing power, which is very important, that's the three main ingredients. Training database, a training algorithm, and then a test database to test the accuracy of the approach. Okay? And that's all with the overview. By the way, I'm going now backwards, so I'm going to start with that. I'm going here and then here. Okay. I told you it's a very short overview, right? Test database. So there are different approaches how to do that. I mean, you already saw, I guess, that I have only one slide here. I'm not going to talk more about this. So usually, when we get a data set, what we do is we split the data set. Let's say 80% training, 20% for testing afterwards. This means that I use the 80% of the data to test my approach, and then I use the 20% to put them in the neural network or the decision tree and test, is this correct or not? How does it classify, right? Other could do 70-30, other could do 90-10, it's up to you. What my main point is here is that test database is very important, right? Because everybody is comparing their approaches based on how well they perform, how accurate they are, right? But the question is, what kind of data do you put in there? And I don't claim that in our papers we do that better than others, right? But it's very important. It's crucial to have the right kind of database, which means you have to have data that span the whole spectrum of your possible, search space, feasible space, stable space, whatever you want to call it. Okay. So test database is important. Right now, what we are going to doing a hands-on exercise, you don't need to split your data into test and training. The toolboxes do that for you. But in general, if you can get your hands on real data, it's important to have it tested there. And still, you must make sure that actually they also cover, they're not only safe points. I mean, for power system security, we're not talking only about safe points, and that's the problem with the currently available data, right, in power systems. So power systems are so reliable that most of the operating points are safe operating points, right? You get only a few of those that are outside the safe region. So you need simulation data to simulate situations that you are close to the boundary or outside the boundary. And then, so to get the simulations, you need good models. So it's a whole process, right? I cannot stress this enough. Keep that in mind. Test database is important. Nothing else to add here. So we started. So I want to have a break, let's say after 45 minutes that I'm talking. I think we start a bit later. So I'll take 10 more minutes, right? And I think in 10 more minutes, I will do the next chapter. And then we can take a break, right? If it doesn't take me 10 more minutes and it takes me 12, I hope you will hang in there. Good. Now, we have the test database. Good. We talked about that. But let's go a step, take a step back. So let's suppose we have the training database. We have to train a neural network or a decision tree algorithm. So I have here a first slide talking about decision trees and neural networks. How many don't know about decision trees or neural networks? Good. OK. So this is the only slide I have. But I think I can explain that well. I trust myself. If you don't understand, just ask, right? OK. Decision trees are relatively straightforward. It's like an if-then-else clause, right? So I actually used that from one of our papers. We have line flows, and we try to assess the stability. So we say here that if the line flow between, this is for the 14-bus system, by the way, if the flow between bus 4 and 3 is more than minus 17.8, this means that it's in the opposite direction from 3 to 4, right? Then is it bigger than that? Yes. Then we're not safe. End of story. If it's more than that, then I have to take another line. And what decision trees do is, when I train them, I try to split the data in two. So I start with a large data set. I try to find what is the best separator, right? So you give a set of features. I want to separate the data based on line flows. Which line flow is the most appropriate? And I mean, behind that, the algorithm is running some optimization to identify, so where should I draw the line? And which feature should be that was going to identify safe from unsafe, classified in the best possible way. And then as long as I do this and I split the areas, then I know that this part, I have discarded that this is unsafe. Then I focus on the other area. And then I try to split that area in two more areas and say, is it safe or unsafe? And I'm going like that, right? I mean, this is what happens here. Of course, you can have another tree going down here. Is that clear? Any questions on decision trees? Good. Neural networks are a bit more sophisticated. That's also why I guess I think they appeared later, but also why probably they are more powerful in some ways. One more thing. So the good thing with a decision tree is it's very, let's say, straightforward for operators and for us to understand, right? These are actually real parameters. We understand what's going on here. I can understand how this is split into different parts. Please.
Do you consider link 3 to 4 twice when you do that? Or it's just an example?
Here? Yeah, because this line is very, very crucial. So the question is that I consider 4 to 3 at least twice, right? Yeah, but this is very crucial. So if it is if it's less than minus 71.2, then I have to check, is it also less than minus 74? So this is the first separator. Then I check a little bit further. Is it even more than that? And then it's safe. So I do that gradually, because between 74 and 71, it might be safe or not. I don't know.
No, but there's no other exit.
That's true. I guess I have to go back to the paper, but this actually works very well. Yeah, I think this is only part of the tree, to be honest. Yeah. Okay. Yeah. Yes.
How do you know which lines you should put in these conditions?
The algorithm is going to tell you which lines you're going to put in the conditions. Okay. But you say that you want to classify based on the line flows. That's what you have to tell them. Other questions? Good. Okay. Neural networks. Neural networks are actually a combination of linear weights and activation functions. Okay. So what happens here is I get some data point. I multiply that with W. This is a linear weight. And then I pass it through what I call an activation function. This is something nonlinear. And you have a range of possibilities to pick from. And also in your hands-on exercise, you will have a range of possibilities to pick from. Okay. Deep neural networks, they actually use ReLU. ReLU means rectifier linear unit. It's nothing else than a max operator. And I think also in MATLAB it's called POSLIN because you get, it has this response, right? So this is xi, right? Or if you want wxi. And this is my ui. Okay. So ReLU works, if it's anything negative, my output will be 0. And if it's anything positive, it would be equal to wixi. Okay, this is. So the max operator, what it does, the max 0 and the, so I have bi there to be complete. Bi is a bias. It's just a linear function, right? So I have a data point xi. I multiply that with some weight. And then I check, is it negative or positive? So imagine that the weight can also be negative, right? So I can get a positive input, negative weight, and I have a 0 output. The weight is something that I will define, or actually my algorithm, during the training. The major challenge for all neural network training algorithms is to figure out how they should determine the weights to fit the data. It's very close to the linear regression, and I'm going to use that example very soon, that Pierre was talking about today morning, right? And I'm very happy that you were exposed to that. Questions? It's fundamental, guys, so I want you to... Are there any questions? Is something unclear? Okay. Let's see how, yeah, please. Let me, yeah. You can throw it to me. Oh.
So there's only a connection between nodes of different layers, and nodes in one layer are not connected.
Yeah.
Okay.
Yeah. Questions? Good. Okay, so I mean, neural networks by themselves is like, I don't know, 2 full semester classes, or I don't know how long, right? And now we have just a couple of minutes, so I'm only going to focus on a couple of things that I think they are important also for your exercise, and also to get into this kind of jargon, so the terms that are used in training a neural network. So I'm going to talk about these 3 things. Okay. Let's start with the first one. Batch size, iterations, and epochs. Because you are also going to see that during the training of your neural network. I'm using a linear regression. I mean, you did that, probably you did even more advanced things during your hands-on exercise with Pierre. Okay. A set of data, I want to estimate a line. So ideally, I want to enter all my data and try to estimate the line across all this data, right? Because the line must fit all of them. The problem is that if I have a lot of data, it's impossible for my algorithm to run, right? Computationally impossible. So what I do is I run that in batches. So instead of having like millions of points, I split data, I don't know, depending on the application, 100 points, 1,000 points, depends, I don't know. So, but I split that in batches, and I try to train that based on that, and I do then iterations. So the total number of data is actually equal to the batch size times the iteration. So let's say I have 1,000 data. I split that. Here I have 200. Yeah, 200 batch size of 200. I do 5 iterations, and so I estimate the W1 and W2 for the first 200. I keep those. Then I do the second batch, and I update my weights, and I do that. Okay. And then one epoch is when my whole data set has passed through the training. And it has been shown that we need to have several epochs. So we need to pass the data set several times through the neural network to achieve a good performance. Questions? Okay. Second point I want to make. Loss function. So as Pierre was saying, I think you used least squares in your previous example. In general, we need to identify a way to determine the weights. So we need to minimize the function. We need to minimize the estimation error, right? There are different ways to estimate the error or the loss, if you want. So here I have it. I mean, you have been through that, so I don't need to spend too much time. And the question is, what cost functions shall we use? So here we're focusing on power system security, which means classification, safe or unsafe, right? So there are a series of different cost functions. You can look them up. What we're going to use, or what is being recommended to use, is cross entropy. And I want to talk a bit about cross entropy so that you get to understand what's going on. It looks pretty complicated, or it doesn't. Has somebody used cross entropy before? No? Okay. So this is how this looks like. Let me explain. So this is my true class. So let's say 1 is safe, 0 unsafe. So I have a set of data, a database, right? My operating points, and I have already classified my training database to safe and unsafe. So 1 safe, 0 unsafe. So I have that in curly brackets because it's either safe or unsafe. I have already decided, right? The problem is that the neural network won't tell me exactly 0 or 1. It's going to take an estimate. Okay. It's going to be somewhere between 0 and 1. And this is going to say probability. If it's closer to 0, then it's probably unsafe. If it's closer to 1, it's probably safe. Okay. So that's why this is square brackets. Okay. So this is my, I take each data point. Actually, I have that everything in my next slide. You can look at it. So I take my, for each data point I have, I take my real value, and I take my estimated value from the neural network, and I also take the opposite. And then my loss function is the average over this, right? I take the sum. Okay. And this is also what I talked about. Now, why the minus? Yeah, you can use the, please, over there.
The data is between 0 and 1, so log's going to be negative.
Right. Exactly. So my data, my estimate data is between 0 and 1. Log of something between 0 and 1 is going to be negative. Okay. And the same here, because 1 minus 0, 1 is going to again be somewhere between 0 and 1. Clear? So the log is going to be negative. And I want my loss function is like a norm, right? My norm is positive. So I minimize the norm. I minimize that something is positive, and I want to bring that to 0, right? And I put a minus there to make sure that this is positive when we're talking about classification. Good. Questions? And this is how it looks like. So let's suppose that the real class is 1. And now that's what the loss would be. So what my, the loss or the cost, whatever you want to call it, is going to be based on my estimation. So if my estimation is close to 1 or even 1, here it actually crosses 0. Or it will never cross. Or will it? Yeah, it will. So this is 0. So the loss is 0 if I have done the right estimate. So my estimate is 1. The real class is 1. If my estimate is 0, you see that this will go to infinity. Okay, this is how it works also the opposite way. Last point, evaluation of the performance. So we talked about the test database, right? And what we need to do now is to assess the performance of our algorithm. And what we use is this confusion matrix, which probably is confusing as well. But I mean, if you spend some time with it, then it's going to be more intuitive. But even for me, sometimes, I mean, all these true positive and negatives. But it is simple, right? In the way that if the target class is 1, the output class is 1, we have a true positive. If the target class is 0 and the output class, or the predicted, is 0, we have a true negative, and the rest is false, positive, and negative. I'm going directly to the next slide because maybe that's a little bit more intuitive. We're talking about power system security. If it is the operating point, if it is actually safe, and if it's predicted safe, it is a true positive. If it's actually unsafe and it was predicted safe, it's false positive, right? So it is unsafe, but my neural network said it's safe. This is false positive, right? And false negative is the opposite. It is actually safe, but my neural network said it is safe. It is unsafe. So, I mean, this is all a matter of definition. I can switch those, right? I can put unsafe here, safe here, and the same here. It's just a matter of definition. This is my reference. 2 more slides, I think. Okay. I want to make a very important point here before we go on the break. And there are different evaluation metrics. Accuracy is what a lot of people have used. I think this is changing, or has changed already, to be honest. So what is accuracy? And that's why I was talking about the confusion matrix. You try all the true classifications, so the true safe and the true unsafe, right? I mean, that were classified correctly. And you divide them over your whole data, more or less. And that's how you evaluate accuracy. So assume 1,000 data points. You have 500 safe and 500 unsafe. That's the real values, right? And here's what your neural network gives you. It's 480 safe, as they should be, but it also predicted 20 wrongly from the safe points. And here, it's 470 correct predictions, but then it also predicted about 30 wrong. So what is the accuracy? Anybody? Yeah. Yeah. 95%, right? 95% accuracy. Very good. However, what I claim, and it's not only me actually, I have read papers and I've seen also different simulations or results of us. So accuracy is not enough. Why? Yeah, can you use the microphone? Could you please pass it to her?
For example, you have an unbalanced data, like 90% of your data it's maybe safe. You are going to have a high accuracy, but you don't.
Very good. Very good. Yeah, that's exactly the point here. So imagine now that I have only 20 points that are actually safe. So I have a very small safe region, and the database we have created for the 14 bus and we're going to give you is exactly like that. It's a very small amount of the whole million operating points you have that is actually safe. Okay. So if you have an unbalanced database, accuracy is not going to do a lot. So the accuracy here is again 95%, but I have actually misclassified 19 out of my 20 safe operating points. And to be honest, I can even do that, let's say, more aggressive, say that my neural network has misclassified all safe operating points, so that it has found no safe operating point and still will get a 95% accuracy, right? So I will get a 95% accuracy even if my neural network would think that there is nothing safe here. So that's why accuracy is not enough. We need additional metrics. I'm not saying replacing accuracy, but I'm saying complementing accuracy. So when you assess your performance, don't use only accuracy, especially if your databases are skewed or unbalanced or whatever. Yeah, that is the last one. So I'm not going to go through all this, but there are different metrics that exist in the literature. We have used those, and we were trying to find a way to visualize them, so we thought maybe a radar chart is a good way. I'm not sure, to be honest. But we couldn't think of something better. What I just want to say is this, which I find very interesting, is for binary classification, safe or unsafe. Okay. So you use this formula here, that's fine. But what is nice here is the following, that if this Matthews correlation coefficient this goes from -1 to 1, right? If it's equal to 1, this means that the neural network or whatever neural network behaves as predicted, right? So it classifies safe as unsafe and the ones that are not. But if it's around 0, just give me a moment. If it's around 0, this means that it's completely random. So you might have an accuracy of 90%, but this can tell you, or maybe 90 is too high. But anyway, this can tell you if flipping a coin is equally good as your neural network, or your neural network can do that better, right? So it's a nice metric to understand. I mean, because high accuracy doesn't always mean that, you spend so much time training something, and then in the end, if I flip a coin, I probably have the same probability to find the right result, right? Yeah. Can you please pass the, yeah.
So you mentioned at the beginning of the presentation that it's very important that you operate safely, otherwise it can be very costly. So first question would be, is there a way to, differentiate between different parts of these confusion metrics on how costly these parts are? And the second question would be, can you actually adapt your loss function, your cross entropy, to account for this?
Yes, yes, and yes. So, and that's what we do, right? So what you really don't want is to classify actually unsafe as safe, so the false positive, right? You want to avoid that, because this means that your neural network will tell you it's safe, but it's actually unsafe. So what we do there, we add this kind of epsilon. There are different approaches, but you can change the way that this class is classified to put an extra weight on not classifying actually unsafe points as safe. This reduces your accuracy in general. Okay, it does. But it's much better to classify an unsafe to miss a bit, let's say, of the actually safe points and classify them as unsafe than the other way. Okay, so you can do that. Other questions? Okay, I think you all deserve it. Please.
When you're taking the data, what's data you are taking for classification?
Say that again?
Voltage is a current.
For classification?
Yes. And how many dimensions it has, like?
Depends on the system, right? What we have done up to this point for decision trees, as I say, at the moment, we focus on n-1 security and small signal stability. And for decision trees, we take the line flows because we think that, we do some applications with markets, and we think that this is actually the best way to go. For neural networks, we take, again, active power flows, so line flows, reactive line flows, and voltage drops. Again, we're focusing on the snapshot, and we're trying to identify if this is n-1 secure and small signal stable, right? There are many different things you can do. We tried those. They seem to work, but of course, we're still at the beginning of looking at this. Questions? Yeah, can you?
As you mentioned with the false positive before, it's very costly and you really don't want to have that. So you said you can adapt the weight in the loss function so that it penalizes a lot.
Yes.
But the problem is, the biggest your problem is, the biggest you need to have a weight, which penalizes that. So how do you define this weight, and how do you know it's big enough so that you will never have a false positive? Shouldn't it be binary or something?
No, it's actually a bias that you put in the classification to have, so in the loss function, so that you penalize more, let's say, because the loss function is assessing. So if you go back, so the loss function is assessing this, right? And you try to bias it towards not classifying false positive. Okay. About the second question, you cannot be sure that you are going to avoid all false positives, right? And I'm going to claim, I must be careful, but I'm going to claim that you might never be sure, right? We have started like the past few months, but I mean, the community in the machine learning, they started working on these verification methods, right? The last 2 years, where they try to verify areas. So I cannot tell you if you are on the boundary. Maybe I cannot verify that point, but I can verify larger areas of my operating space if they're going to be classified safe or unsafe, right? And that's what I'm going to do. If I can ever be able to classify or to verify the whole behavior of the system, I think we're pretty far away from that. But I mean, there's a lot now growing interest into this. That's what I can say.
So then, concretely, how much do you estimate the weight should be in big systems?
So you have it's trial and error. What do you mean the weight? I mean the bias, you say. You have to try. And you check the accuracy and you check the number of false positives you get. I mean, yeah, how else? Maybe you can come up with a good idea. I don't know, a good method. Yeah, and I mean there are some kind of approach you can follow. But how do you tune a PI controller? I don't know. It's so there are some methods, but it's a bit of heuristics. Yeah, I don't think there's a complete answer at the moment. Okay. I just saw there's one more slide, but I'm going to do that after the break. Okay. So let's. Can we be back here at is it 4:05? Yeah, 4:05. Sure, sure.
Well, I'm Sarah, and I'm doing my research in like trying to predict the deviation of the system, like if it goes -1 or 1.
Deviation of what?
Yeah, if the system is imbalanced, TSO, like the general country, so in order the agent market can use avoid the penalization for deviation.
Okay, for reserves, or let's say.
Yeah, for the.
You have a schedule, let's say, and you don't want to deviate.
If you are less of generation, you have to. Okay. So I've tried like some algorithms, and my question is like, I mean, I know that this is like a cooking stuff. You have to train it, but is it better maybe if I using more data in order to the algorithm to learn from that amount of data, or maybe because maybe the code used 4 years ago is not, it doesn't make any sense to use it right now because the distribution is different. So is it better maybe to use less data, but more recent data?
So it's either using more data from that time or
the
less data.
But less.
Oh, I don't know.
Cross-validation?
What's that?
Cross-validation?
Well, it doesn't work as you can use them both, but it's like.
But can you use test in different ways and see how well you do?
I know.
So you start with some data and you train it, and then you say, if I add data, how much data far back in the path? When does it perform worse, basically?
Yeah, so it's like kind of trying.
Yeah,
right?
yeah. I don't. Yeah, and I mean, please go ahead.
Sorry.
No. It's exactly. I mean, because you can never know. I mean, it's different problems have different types of data. But yeah, please.
So there's also this like I don't know. We used to play around with some TensorFlow, like, and then you can set weights to your data, to your batches, basically.
Yeah.
So then maybe you set smaller weights to batches that are further back.
For the past data, and then use more weights for the recent ones. Yeah, okay.
That's like putting a prior on your what you know about the data.
Yeah. Okay. It's like the weight, Okay.
Yeah.
Really interesting.
Thanks.
Yeah. You mentioned that you had like when you worked with decision trees that you've seen that lines are very important for market applications.
Yes.
What was that? Can you tell me?
We also have a short presence about this. But so markets, if you think, I mean, like flow-based or even in the. So I have to somehow limit my space to the safe space, right? And there are different ways to do that. One way is to limit the generation output. So that I can say that the generators are only allowed to produce from 0 to 10, because if they go to 20, it's going to be unsafe, right? But from the regulatory perspective, you are not allowed to tell a generator that they are not allowed to produce as much as they want. But what I can do is, for safety reasons, I can limit the power flows on the lines. And that's why we use those.
Okay.
Okay. So you use the power flows on the lines because this is reasonable for the market application. That's also what is being done at the moment.
Yeah.
All the operators send the constraints on the lines in order for the flow-based market coupling to operate.
Yeah.
Is that
it's
clear?
also nodal, isn't it? They can send
Also
also to nodal.
Yes,
Yeah.
yes, yes. But I mean in Europe.
Yeah.
In the US, of course, they use the nodal. Yeah.
Okay. Okay. Yeah.
And because the thing is that the market is still solving a DC optimal power flow, but you need to be N-1 secure. So you don't use the real transmission limit, right? You always use something different because you want to make sure that whatever flows through that line because of the market, the system is going to remain N-1 secure. So you have to constrain your system by constraining the line flows.
Yeah.
Right?
I'm not from actually
engineering
background. How does it work when you constrain a line? Because it's AC coupling, so the line, I mean, the electricity will flow, whatever, even if you want it or not. Or how does it work?
So the thing is that you model it. So the operator models it with AC, and they check how this works, and then they make sure so you can infer, let's say, proxies for the DC power flow to make sure that nothing will happen.
Okay.
That's the same thing that we did in our paper in order to make sure that to make this connection between AC and DC.
Okay.
So imagine that if you really constrain it, if you get it to 0, then you are N-1 secure, right?
Yeah.
Or maybe not.
So if I reduce my capacity on the line for 50%, how do I make sure that actually not more than 50% is passing that line?
You don't, but what happens is that you only allow 50% to be traded in the market, and even if it goes to 100, then you are safe. That's what happens.
Okay. Yes. Yeah. Okay.
That's how but you leave this margin, the safety margin.
So you strain the market, basically.
Yes.
Okay. Question about this, using image recognition techniques to kind of. Have you worked anything with graph convolutional networks?
Not yet, but so I mean the pictures that we create it's like matrices that have they represent graphs.
Yeah.
Because we can represent the graph of the matrix.
So there is actually starting, and I just read a little bit, and it's starting to become more and more. And that what you linked as well from NIPS 2017, they talked about it in that video, like graph neural networks, and it feels like a good application for power system because they are
I think so too. Yeah.
a little bit more like graphs. Yeah.
Yeah.
You haven't tested it out.
No, not yet.
Okay. And last question. So the decision trees. I mean, you said that you have a lot of different, input variables.
You can have, yes.
Yeah, and then do the decision trees to scale with a lot of variables, or?
So it depends what kind of variables you want to use as classifiers, right? If they scale, the more variables you have, but it must be, I think, the same class.
It must be.
No, you can have different. The larger the number of classifiers.
Yeah.
Let me think.
Classifiers. What do you mean by classifiers? Do you mean decision trees?
No, I mean the number of variables that you have as predictors.
Okay. So predictors. Okay.
Yeah. So the number of predictors. The more they are, this means also the bigger. The more difficult it is. Yeah, the bigger
higher dimensionality of input space. Yeah.
So, if that works.
So the question is if it's because this algorithm is like splitting these decision trees. I read some papers about this, XGBoost, and it seems to be actually, when you come up to a large number of variables, it's very hard to find these optimal splitting points in this high-dimensional space.
It's definitely, at some point it becomes intractable, right? For these systems that we're looking at, and so I don't think that power systems are yet at this point, up to 160 bus that we have checked, because the major challenge is to create the database. And I have the impression that this will become more difficult when we go to higher dimensions.
Did you use any packages for decision trees?
Yes, it's from the machine learning and pattern recognition from MATLAB, decision trees we did only in MATLAB, but the neural network is also TensorFlow.
Okay.
Yeah.
Okay. So we played around a little bit with XGBoost, and the Microsoft also has a decision tree implementation, which is supposed to be scale much better than the other ones. You can test that one. It's called the Light GBM.
Light GBM. GBM. Good.
Yeah.
I'll keep that in mind. Great. Thanks a lot.
Thank you. I have a question about training scenarios. Are you using deterministic training scenarios for contingencies, or it's a kind of probabilistic?
No. It's completely. So it's This happens. Is it safe or unsafe?
You know, I'm talking about because you can train your neural network with probabilistic scenarios or deterministic scenarios. For instance, using something like Latin hypercube sampling to generate a pool of scenarios, or something like deterministic n-1 contingencies.
So we have used LHS, the Latin to sample our database of operating points to focus on the really relevant scenarios. But these are all deterministic, right?
Which
the scenarios that then we test, so we take a probability which scenarios we're going to assess, if it's safe or unsafe, in order to have it in our database, but that's it. Is that what you ask? Or?
I think it might be good to generate training scenarios based on their probabilities instead of a deterministic set of scenarios.
So
know, for instance, something like scenario generation in reliability evaluation, because in this case...
Let me interrupt you. There are two things because I'm trying to understand. One is which operating point you are going to assess, if it's safe or unsafe. The other is the probability of that operating point to be safe or unsafe. Which of the two?
Both of them.
Okay, so we do take into account. So we do take probabilities for which scenario to assess, but then it's deterministic if it's safe or unsafe. Yes, you can do probabilities. This will take much more time for our assessment.
But if you are,
and I'm not sure
if you are going to use a scenario generation technique, because for instance you are considering n-1 contingency. But if you want to consider the entire uncertainty spectrum, you need a scenario generation technique, something like Monte Carlo or Latin hypercube sampling, to consider multiple contingencies instead of single contingency.
So if you read our paper on efficient database generation, I'm going to shortly talk about this. We try to do something that works better than important sampling, at least. And I think that was the best that we found in the literature.
Great.
So you can,
Thank you.
I just have a very short question, because you said you were checking for small signal stability.
Yeah.
Does that mean that you have a full small signal model of the...
Yeah, of the 14 bus and the 162. Have a 6th order generator model for each generator, AVR, PSS, and governor.
So then it's no fast dynamics or...
No.
Because that's what we're doing at the moment, or Roche is doing at the moment.
For creating these databases or for...
No, we're looking into that, then how fast dynamics are in the inertia systems, and then we realized that we need to include line dynamics and all these things for future systems.
We do that as well.
And so then it gets huge to assess small signal stability.
It's going to be very, very difficult. Small signal, Yorgos, so my PhD student, has included the line dynamics. And he does assess small signal stability. But this for the North Sea Wind Power Hub, which it's a small system, like 3 or 4 buses, because we're talking about 2 HVDC. So I don't know how, I haven't asked him about the computation time, to be honest, and how this scales up. But you're very right. It's going to be immense. And
no, I was very surprised hearing that you're checking for that. Okay.
But, and I would have liked actually Yorgos to discuss with you, but it was never. I was thinking maybe tomorrow, but then I realized that you're limited day. But it'd be nice, I think, to have some kind of interactions. He has with Uros, and I think it'd be nice to interact.
Yeah, I'm definitely open. I'm also working on fast dynamics. As I told you, I'm working on the load side. But we can maybe organize some.
Yeah, either a visitor can also. With Uros last time we had like a Skype call. We can do something, and we can define a topic. One more thing. We're going to organize 20th of September a migrate with our multi-DC, it's our project meeting, and we want to. You are very welcome to come. We can discuss. September.
Okay, I'm gonna check.
And I'm also. And the 19th we're going to have a presentation of what we're doing here. So if you can come for 2 days, that would be nice. But the 20th will be private only for us. Also with Patrick, I'm coordinating that to discuss about what the groups are doing and how can.
I will definitely note that in my calendar. And I'll probably drop you a mail then.
Great, thank you. There was one more person waiting to ask a question, but I don't remember. Is it covered or? Yeah. Okay. Good. So I want to leave at least 1 hour or more for the exercises. But the good thing is I don't have too many things to say more. I have one last slide here, and then I have, let's say, 2 short parts about new insights about some of the work we're doing and how, and maybe this can give you some ideas. Okay. Also, I mean, besides your ideas, what's important for us is to get your feedback, what you think, or any comments you may have. Okay, so this is the last slide, and this is going to help you for your implementation. 2 things. Dolores said that already. Normalization is very helpful for training of machine learning algorithms. So instead of putting, let's say, a set of generator set points that goes either 10, 100, 1,000 megawatts, it's better to normalize that over the Pmax. Okay. Neural networks work better or are getting trained better when they get a normalized input. And we do that, participation factors for small scale stability and many other ways. Also for optimization, the constraints are always normalized. So keep that in mind. The second is that it works better if you do the one-hot encoding, as it's called. It's not hot, it's just an encoding that goes like this. So safe and safe, this works for binary classifications. Have safe and safe, it's either 0 or 1. It's better to have one vector for each class. So then, for example, my x1 is unsafe, right? Which means that safe is 0, unsafe is 1. It's like binary numbers, right?
What's the reason for that?
It works better for the classification when you check It works better. But it's a good question. Maybe I have to check why it works better. But the truth is it does. Okay.
But isn't it that you want to have, you need to make the sum. So it is that you give the whole vector to the loss function. Isn't that you do vector or tensor multiplications in the end to get the loss function? So when you do one hot, one hot representation is the same as saying safe and unsafe.
Yeah. But it works better for the training. So you give that, the training database must have your operating points and if it's safe or unsafe, right? It's better to classify the safe or unsafe. When you train, you already know if it's safe or unsafe, right? It's better to classify safe or unsafe like this. It's exactly the same, but it's better for the, okay. So that for one class, this is 0, for the other class is 1, instead of trying to figure out. Okay. Yeah.
I think because safe is not larger than unsafe. So if you put it in one category, like there's kind of a ordering between.
Yeah, that's correct. So what you say is that there's no ordering. So it's because they do this kind of linear regression, it might somehow think that this is, let's say, bigger. 1 is bigger than 0. But what we want to say here is that it's really, it's a different thing. Okay, very good. Yes, thank you. Comments? Good. So we talked about test database. We talked about training algorithms. The next step is about training database, right? And to be honest, for every application is different. I'm going to talk about power system classification with some focus on security. And there is some work in there. We think that there is not a lot of work in that. So I think that there are many applications in power systems that are trying to develop new neural networks or develop new approaches for decision trees. But we haven't seen a lot of work on how to generate a database, because what people would do probably is just run the simulations and try to get this data, and this is my database. But if you really want to capture the whole area, right, to understand what is safe and unsafe, this is a challenge by itself. And there are some ideas, I mean, there are papers out there with importance sampling and other methods, but we are far away from getting something tractable that we can understand for the whole. Let me tell you that, for example. We looked into the 162 bus system. 162 buses with 10 generators. It's impossible to find out for a single load profile to assess all the possible operating points. Okay, it gets intractable very fast. Okay? Very big, very fast. Okay, we did that for the 14 bus, and that's the database we give you. And if you see, it's 700 megabytes for 2 databases that you can download. I mean, you need to use that for your hands-on exercise. Right? Good. So there is a motivation behind that. So one motivation is, of course, that we very rarely have our hands on real data, except if you are at RTE. But the truth is that historical data are also insufficient. Okay. So the historical data have very few in unstable cases because power systems are usually operated as stable. So if you really want to explore what is your room of possibilities, what's your space, and where can you move, you need to have simulations, and for that you need also accurate models. But this is another discussion that is not, it's out of the scope. Good. So I'm going to talk about this work here, which is ours, just to give you some ideas, because I think it's the latest paper out there dealing with this, at least from what I have seen. And we think that it does some things better than others. But to be honest, I mostly want to give you some insights of how we can apply different things here. Because data has been a lot associated with statistics, right? And trying to get some probabilities, try to get good scenarios. I mean, Pierre is one of the gurus there, right? And I think many of you do something related to that. But we took a different approach. And so here is the, okay, good. First thing, as we said, we want to focus on the boundary, right? So we really want to understand, so that was our initial idea at least, when we cross from stable to unstable. This is real data from the 14 bus system, right? This is the 2D projection. I mean, the whole space is, yeah. So we really want to check data that are close to this high information content region we say that is between the safe and unsafe points, or stable and unstable. Good. I mean, the region is non-convex, which means that after all, we also need to take some points inside, but let's say that's important for us to identify where this boundary is. So this is point number 1. So how do we do that? And then Andreas actually came up with this cool idea, convex relaxations. Have you, who is not familiar with convex relaxations in power systems, or in convex relaxations in general? Just to understand how deep I should go. Yeah, good, okay. So what a convex relaxation is that you have this non-convex stable region, right? Which is characterized by a set of nonlinear, non-convex equations, right? That's why it's a non-convex region. And what you try to do is you try to relax these equations into some convex functions. It has found, let's say, over the past 7 years, a big, has created even a field, I would say, in power systems, convex relaxations for power systems. So what we try to do here is we try to use some of those concepts, right? So imagine this. So non-convex region, these 2 points are safe, the others are unsafe. I'm approximating this region with a convex relaxation. So what I essentially do is I relax my constraints to something that's convex. And I'm talking only about the steady-state power flow here, steady-state power flow only. Because the first thing is you must satisfy the steady-state power flow, so you must be in here, and then you can check about stability, right? You must satisfy the limits, and then you can check about stability. So the first step is just steady state, and we use STB for that. Okay, so convex relaxation. So this gives a certificate that any point that is outside this area, like this one, is definitely going to be infeasible for the original area. Clear? Is that clear? Good, because that's the main takeaway, actually. So this is unsafe. And then what you do is you formulate an optimization problem, find the minimum distance, so until it becomes feasible, right? So what is the minimum? So I have the operating point, and I want to move to another operating point. What's the minimum distance where my relaxed equations will be satisfied? So I have an optimization that says minimize the distance, subject to all these constraints are satisfied. As soon as the constraints are satisfied, I'm in the region. Actually, I'm exactly on the boundary, right? And what I do is I take this ball. Here's a circle. In 3D, it's going to be a hypersphere. A sphere. In more than 3D, it's going to be a hypersphere, right? And I discard everything that's in here. So what I do is I do this Latin hypercube sampling, which I was discussing with somebody. But I just sample, right, probabilistically, my whole search space. I first check if this operating point is infeasible for the convex relaxation. If it is, I just take the ball that actually is adjacent or tangent to the region, and I discard all these points because I know these are infeasible. I don't care about this. So it's very easy. I cut parts of my space, and I don't need to look into that. Yeah, there's a question.
That you're trying to use as a convex proxy for the non-convex stable region. Is that the shape that you're using, or you're using, for example, convex hull just to?
No, it's not. It's not going to be a convex hull like a polytope.
Like a polytope, yeah.
Probably also not an ellipsis though. I don't know the shape it has in our multidimensional space. Probably.
So how do you characterize it? Maybe that would be a better.
Yeah. So we have the AC powerful equations, right? And we relax all the non-convex functions by. So it depends. I mean, if you do a second-order cone, you have to make an equality. Whatever is equality, we have to make it inequality. In SDP, you model everything like that x squared. So x squared, you model it as a W matrix, right?
Mm-hmm.
Is it clear? Good. And then you just have to drop the rank 1 constraint.
Mm-hmm.
So yeah, whatever shape you get by dropping the rank 1 constraint.
Oh, okay.
Okay. But it is a convex optimization problem, and that's the main. So the convex optimization is actually a relaxation of the. Yeah. So here you have all the constraints that satisfy that characterize this region, and then you just relax it. Okay.
Okay.
Okay. So this also how this is real data. Andreas sitting over there, he's going to be helping us with the exercises. That's he actually generated this image. So this is how it looks like in 3D. This is also a 3D projection. Okay. So you see that there are small balls, and there's a bigger ball here, right? Different, and then the white area is the safe region. Good. Now, what we're also working on, and this is going to be submitted soon, is a smarter idea that, if you think about it, it's strange that we didn't think about this in the first place, but Andreas came up again. So instead of getting the ball, getting the hyperplane, right? And you can see that instead of actually discarding, let's say, 5, I mean, here I can get so much more. And our initial results actually show that. You need much less points, and then you can just, because if you get a hyperplane, you are definitely not going to cross the feasible region. Clear? So that's the new that will come up So what I'm trying to say with all this is that there are ways where you can combine optimization, convex relaxations, data-driven approaches, machine learning. And I think that let's say you can get so much more impact if you try to somehow get inspired from different parts or different fields. Okay. There are many different approaches that, if combined in ways that we haven't seen before, they might be much more effective. Okay, and then we also do directed walks. That's what Florian has been working on very, very nicely. So we try with gradient descent when we have the feasible points to move towards the boundary and then try to evaluate as many points as here. And we use parallel computation. So parallel computing, there's a smart way to check for n-1, the critical contingencies, and the variable step size. I don't want to go more in detail into this. But this has worked pretty well, to be honest. So these are some results. So the brute force approach that tries, so what we're talking about here is how many points we have close to security boundary. We have defined a distance gamma around it. So in order to identify 100% of the points for the 14 bus, with just evaluating every point, it takes 500 minutes. With importance sampling, which the approach that we found that was, let's say, the working the best in the literature, is 35 minutes. And with this approach, because exactly we discard a lot of points that we don't need, and we use this parallel computation for with directed walks, we get it in 3.8 minutes. And then for 162 bus, I mean, yeah, brute force is impossible. In 35 hours, we get 901 points close to the boundary. And this can get much faster. This is also discarding invisible points, and also the direct walks work very well here. Good, but there's still a lot of work to be done. This is just the first approach. I think there's a lot of room for improvement. And I think it's also necessary, if we want to apply data-driven approaches, we must get good databases. So we have put this already online, the 162 bus. You get the 14 bus, you can download it over Dropbox. Okay. So you can have access to both. You can use it for training your algorithms or whatever you need. Done. I have one more. So one more insight. And I have 7 minutes, which I think enough. Any questions? Good. So, please, yes.
Because you do a convex relaxation and then you discard stuff on the outside, but how do you know that you don't have like disjoint feasible regions? Like what?
So even if you have disjoint, the convex relaxation is going to cover the whole feasible region. If you have disjoint, so this means that to be completely disjoint, there must be some kind of no, the convex relaxation is going to connect these disjoint regions. So there is a famous, yeah, an example that we use. Dan Molzan has created that. So there is the feasible region looks like a Nike shoes, right? Like this. Okay, that's a feasible region. But then you add limits for reactive power that must be above this. So then your feasible region is this and this. Okay, and then you have two disjoint regions. And to be honest, the true optimum, the way that he has constructed the example is here. But the normal ACOPF finds it's here, right? Because that's where it focuses. So the convex relaxation, what it does is actually relax this constraint and makes a convex region that looks, I don't know how it would look like, something like that, I guess. So this will have to, something like that. Okay, and removes this. And then you find the optimum here. So it's a different, it changes the space, but it definitely includes this. Okay.
If you've got areas in that, on the top bit that's being feasible in the convex relaxation bar isn't, then what do you do with them?
I'm just saying that my certificate is that if it's outside here, so if it's here, my point, it's definitely not feasible. Yeah. That's the only thing I can say, okay. Right? Yeah. Any other questions? Good. One more thing. So I was also talking before about this, what I think there is a lot of interactions between optimization and data-driven approaches or machine learning. So we have already talked about interpretability. Dolores did, right? That's where we can use optimization. We talked about how to train. I mean, we need some kind of optimization for the loss function. This is what I would call a third category. And I mean, I use the same figure here. And I am talking now about electricity markets. Okay. So this is my safe region. I want my electricity markets, so whenever there is a set point defined in the electricity markets, so they must define it somewhere in here, right? So the problem is, though, that this is non-linear, non-convex, or whatever. And what does this mean? So, but the markets run a DCOPF. So they do take linear approximations. So two things. First, they take linear approximations, so they have to linearize around it. And second is, if I want to include in optimization any differential equations, because this has, so even the small signal stability has differential equations in there, it's impossible. I mean, there are some approaches in the literature with some proxies, but it's very difficult, and they don't scale up. Okay. Okay. So if we take now the linear approximations that the markets do, this is for the net transfer capacity. This is the original model that actually the Nordic market still uses, but I hope they will move to something a bit more sophisticated, which means that I identify, let's say, limits on every line, which means that this line can transfer up to 100 megawatts, not more, even if the capacity be 300, right? So if you define this kind of limits, then you always define boxes. These boxes can either be inaccurate, and then you, which means that you land outside the safe region. So redispatching must take place to move it back, and this is what the German TSOs have been doing a lot, with a lot of redispatching loss, right? Or you can be too conservative, which means that you don't really find the true optimum, and you are more expensive than you could have been. There is a flow-based market coupling. This is more sophisticated. The Central West European region uses that. It's a, let's say, a move towards the right direction, where we use some kind of conditional, let's say, flows. So let's say if that flow, so it's linear relationship between the flow, let's say, between Germany and France, and the flow between France and Belgium. So if one is like that, then the flow limit on the other side is going to be something different. But something like that. I'm not going to go into the detail. It's PDTFs. And this is also outside. We can talk about this later. And now what we suggest, though, is the following, right? So we have used decision trees to characterize this region. So you can use decision trees or machine learning approaches, but here we're going to use decision trees to characterize the green region. So you know, you can have an idea about how this looks like. I mean, if your training database is good, and if your decision tree is doing fine, right? But the decision tree is a tree, and mixed integer programming is using trees to identify different ways of using the binaries, right? If binary is 1 or 2, or 1 or 0, right? So I can convert a decision tree to a mixed integer program. Okay. I can convert a decision tree to an if-then-else rule, which is going to say that if my line limit, let's say, is more than 0, then the binary turns 1, and then this happens. I mean, I'm not going to go into more detail, but it's a direct and exact transformation of a decision tree to a mixed integer linear program. So then markets that now use DCOPF, we can still use DCOPF, but of course, I mean, there are the equality constraints that we have to consider. Our paper treats that as well. But what I want you to think about is that then all the inequality constraints, instead of having the simplified equations for the inequality constraints that try to limit the lines, we can use as inequality constraints whatever decision tree tells us in order to limit ourselves inside the feasible region, right? And this is going to be the true feasible region. I mean, if we have trained everything correctly, and if, yeah. But definitely it's going to be something better. So, okay, so this is how this works. We have this, let's say these are real data from the 14-bus system. 2D projection, so it's easy to understand. Stable and unstable region. And then we have the decision tree that we try to train. So this is a stable region, another stable region, and the third one. So these are the three. So with 3 leaves, we can, let's say, characterize the stability. Okay. So and by that, so each leaf is a convex region, right? And then by that, we can actually characterize, we can have a mixed integer linear program. What the flow-based market coupling currently does is that because they want a convex region, they focus on the single convex region, and they tell the market operator that you have to only operate through there, right? So probably what the flow-based market coupling would do is that it's going to focus on this region here. And it's going to discard those because it cannot really integrate them, or it's not cannot, because actually the euphemia, so in Europe, the euphemia algorithm is solving a MILP, is solving a mixed integer program. But they don't want to have a non-convexity, so they only focus on the feasible region that's convex, and that's this one. Okay, so we did some tests, and we were able to expand the feasible space by 22%. And then, of course, we have the quality constraints that we have either to linearize them because they are non-linear in order to keep it convex, or we can use relaxations. And we have used the SOCP, so this is this paper here. And then we can find that the optimal point is in a different region than the original single non-convex. I mean, of course, these are test cases. I mean, there are different examples. But the whole idea here that I want to, let's say, the message, the take-home message is that you can transform decision trees to a mixed integer linear program. So capture the whole nonlinear space by decision trees, convert that to a mixed integer linear program. And we haven't seen that in the power systems community. I don't know if it has been in other communities. We have searched a bit. We haven't seen this connection. But I think it's very, to be honest, I think it's intuitive and nice to use. Yeah. But that's all. And I'm almost 2 minutes. Yeah. Thank you very much, guys. So, any questions? Yeah. Can you pass? Yeah.
So I was thinking about this last part about flow-based market coupling and everything. Would you need to include reactive power flows into the market coupling and the modeling of the, if you use this non-convex region?
Okay, so in the decision tree is trained on a database that includes the reactive power flows, right? And if these reactive power flows, or let's say the reactive power generating limits exceed, are violated, then it's going to say that it's unsafe, right? But the flow-based market coupling does not include that. But what you can do is use a proxy, which means that I can limit my active power flow on the line for the flow-based market coupling to, let's say, 100 megawatts, while I have 200 real limit. And by that, I consider also the reactive power flow flowing on the line, which can go, I mean, I have this safety margin, right? So what I'm trying to do, I'm trying to find proxies, which means that in reality, I have active and reactive power flows, okay, flowing over a line. Which means, let's say that I have a line limit of 200 MVA, and I can have 150 megawatt flowing and 50 not 50 megawatt, it must be the, whatever, but you get the idea, right? It must be the apparent power, it must be 200. But what I can do is, if I think that I'm going to violate the limit because of my reactive power, I can limit in my market algorithm the line to 100 megawatts. So whatever happens, I'm not going to violate in real life. Was that clear, or shall I say it again?
Yeah, I think so. More or less.
More or less, yeah. But, okay. Yeah.
So if decision trees and MILP is like equivalent, why can't I just solve the equations with the MILP and then you store it in a big JSON file?
So the problem is that, I mean, the decision tree infers also from differential equations. So the small signal stability is differential equations. And you can, I mean, yeah, if you can find a good way to represent that with a MILP, definitely. But what I'm saying is that the way to infer that with a MILP is to use a decision tree, because there is already methods there that can do that. Yeah.
How can we face the problem that the topology of the grid can change over time? I mean, if someone builds a new line, the previous assessment are not valid anymore. Is there a way to like transfer the learning from all the networks to new one?
So there are different ways to do that. First of all, you can train different decision trees, right, for different topologies. I would never claim that one decision tree can capture everything, right? So for different topologies can capture different decision trees can capture different topologies or even different parts of the operating space. This is number one. Number two is there is some work from RT, Benjamin Donneau, that's doing some things with neural networks. And the idea there is, they want to integrate n-1 and minus k. But the idea there is to train a neural network to infer, let's say, line flows from an input of generation. And they activate or deactivate parts of the network based on the topology. And the idea is that you train for n-1, and then you deactivate parts, or you activate parts for different topologies, but then n-2 is just activating 2 of those, and you haven't trained for n-2, right? So there are some tricks. It's very, this is now everything is happening. So there's still a long way to go to find something that works well in many cases. Okay. Other questions? Good. So if you want, we can take a break. But we have the hands-on exercise. Have you downloaded the database? Good, because this is 700 megabytes, and I don't know if our Wi-Fi here is going to support everybody doing that at the same time. But at the same time, so what we have here, so first of all, Andreas, please come. So it's Andreas and I was talking about Andreas during the lecture. He's a PhD student, we're working together here. So we have one code for neural networks, one code for decision trees. We also have a text describing what are the tasks. The idea is that you take this code and there are things that you have to fill in. And you have to figure out how to do that. Okay. If you are tired, you can take a 10-minute break. We can come back. We are going to be here until 5:30. You can, yeah. Thank you.